Lesson 7-3, Logarithms and Logarithmic Functions. Let's take a look at the exponential function, f of x equals 2 to the x. Here is a table that will give us this graph right here. And notice we do have a y-intercept. Now I'm going to make this a y, and then I'm going to exchange x and y, and I have created the inverse. And when I've created the inverse, I have another expression that expresses this exactly the same way, and it's called y is equal to log base 2 of x. This is a new symbol that means this. Just like y equals x to the third power, our inverse is y is equal to cube root of x. Cube root is a brand new symbol. This is a brand new symbol that means inverse for this exponential. Now, it is going to be a reflection across the y equal to x line, and all the x's and y's are going to exchange places. We're no longer going to have a y-intercept, but we're going to have an x-intercept. So this new inverse function is called a logarithmic function. We write it y is equal to log base 2 of x. Now let's go ahead and practice going from a exponential to a log expression. And notice that this is the base and the subscript is the same base. The exponent is now going to be isolated, and 8 is going to be what we call the argument of the log. So one more time, this is the base 2, subscript 2. The exponent is now going to be isolated because a log expression is isolating the the exponent. Okay, and here is the definition. There is a log expression that equals an exponential expression that equals a log expression. So we're going to practice going back and forth with these two expressions. First one is to go from logarithmic to exponential. So here is the base, and here's my base. This is my exponent, 2 to the third power, and 8 is the argument, and that equals 8. And that is a true statement. 4 is the base. The log is the exponent. This log expression represents the exponent, -4. And then here's the argument right here. And that 4 to the -4th power is 1 over 256. Let me start from scratch. This is my base. This is my exponent. And it equals the argument of the log, which is 16. And that looks correct. This is my base. This is my exponent. And it equals the argument of the log, which is 729. Your turn. And here's the answer. Your turn. And here's the answer. Let's try going from exponential to log form. Okay, so this is our base. And notice that my subscript has the same base. My exponent is now isolated, and this is my argument inside the log. Here's my base. That is the subscript. 1/2 is isolated right here, and then 2 will be the argument of the base. So let me show you from scratch. Log, and my base is always the same as the base of the exponent, 64, and 3 is now the exponent is isolated. So this log expression is representing the exponent. Log, and my base is 125 of 5, and then my exponent is 1/3. So this log expression is an expression for the exponent. You try it. Here's the answer. Try it again. And here's the answer. Let's now evaluate logarithmic expressions. So we would like to figure out what this is. So I'm going to say equals y. Now this is a log expression. I'm going to change to an exponential expression. And I want to get the bases the same. So 16 is 4 to the second. Pow, pow, multiply me now. Since the bases are the same, we can set the exponents equal to each other, solve for y. So this expression is equal to 1/2. Some of you might be able to do this, get this answer without going through so much work by asking this question. Remember, this log expression represents an exponent. So what is the exponent on this base? Here's the base 16. What is the exponent on the base that you will get 4? And some of you will be able to see that square root of 16 is equal to 4, and that square root is another way to say 1/2 power. And that's what we're getting, 1/2. Okay, so let's take a look at this. We're looking for the answer, so ask this question. What is the exponent? And maybe I can just say x instead of saying question mark. What is the exponent on 3 that you'll get 81? And then some of you might be able to see that the answer is 4. What is the exponent on 1/2 to get 256? Now this might not be something you can do in your head, but we can change them to the same base like we saw up here. 2 to the negative 1 to the x is equal to 2 to the 8th. Pow, pow, multiply me now. And then we can equate the exponents, and x is equal to negative 8. So this expression is the same thing as negative 8. Your turn. Here's the answer. All right, let's take a look at this graph again, but this time let's go ahead and look at domain and range. So the domain for the exponential is all real numbers, and the range is all positive real numbers. Now let's look at the domain here. The domain is all positive numbers, and the range is all real numbers. So you can see the domain and range have switched, just like the x's and y's have switched. Here's the domain and range for this exponential function, which is b between 0 and 1, and the logarithmic function will look like this when you reflect over the x-axis, and you can see again the domain and range has switched. Let's look at these two graphs and look at end behavior. For this log function, where the base is greater than 1, as x goes to infinity, y goes to infinity. As x goes to 0, remember we can't go to negative infinity, the best we can do is go close to 0, and then you can see it gets really, goes to negative infinity. Now this is a real interesting situation because we can't go to negative infinity. As we get closer and closer to 0, we go to negative infinity. This creates what we call a vertical asymptote, which is x is equal to 0. So instead of the asymptote being the x-axis, it's now the y-axis. Same thing is going on over here. As x goes to infinity, we're going to negative infinity here. As we get closer to 0, we go up. As we get closer to 0, we go up. And that, again, this situation creates this asymptote, which is x is equal to 0. So this summarizes what we know about logarithmic functions. The domain is all positive real numbers for both, and the range is all real numbers for both. The y-axis is the asymptote, and it has a x-intercept, which is 1, 0. All right, let's go ahead and practice graphing. Good 2 points to graph is 1, x equal to 1, and the base, whatever the base is, that would be a good point to graph as well. So we're first going to let x be 1, and so we're going to ask the question, what is the exponent on 5 that will get 1? And I can see the answer is 0. Okay, now I want to substitute 5 in there. And I'm going to ask the question, what is the exponent on 5 that will get 5? And the answer is 1. So I'm going to use these 2 points to graph, 1, 0, and 2, 3, 4, 5. And I know this, remember this asymptote here. And then I didn't get that point very well, but I should have gone through that point. Okay, let's go ahead and do this one. 2 good points to use are 1 and 1/3, the base and 1. I put 1/3 first because it's smaller than 1. And so I'm going to let this be 1/3 first. And so I'm going to say, what is the exponent on 1/3 that will give you 1/3? And that answer is 1. Now what I want to do is substitute, instead of 1/3, I want to substitute 1 in there. So what is the exponent on 1/3 that'll get you 1? And that answer is 0. So with these I should be able to graph. So 1/3 1 and 1 0, and the graph's going to look something like this. Okay, your turn. And here's the answer. Again, ask those questions. 5 to the what power is equal to 1. And you can see that that's going to be 0. And 5 to the what power is going to be equal to 5. And you can see that question mark is going to be 1. And I find these 2 points, and I've got it. Pause. And here's the answer. 2 good points to use are the base and 1. And we're asking ourselves the question, 1/2 to what power is going to be equal to 1/2? And that answer is 1. 1/2 to what power is going to equal this number 1? And that's going to be 0. And 1/2 1 is right here. Let me put that in red. 1/2 1, and then 1 0. So this is the answer right here. All right, let's go ahead and talk about transformations of logarithmic functions. And remember, our H is our horizontal translation, K is our vertical translation, A, when it's less than 0, will be a reflection, and A, absolute value of A greater than 1, it's a vertical stretch. A between 0 and 1 is a compression. All right, so let's go ahead and take a look at how we graph this. Now, I've put the points down for my parent function. Here's my parent. And what I want to do is I want to find some new points here. So I'm going to notice that the x does not change, so it's 1 and 10. And what I want to do is I'm going to, this tells me to multiply by 3 and then add 1. And I'm going to multiply by 3 and then add 1. So let me go ahead and graph this. This is 1, 1. And then this is going to be 10, and then that's going to be 4. 1, 2, 3, 4, 5. Okay, 10, and then about up 4. So the graph is going to look something like that, because we have to, as we get close to 0, we have to have an asymptote. Okay, over here, notice that something's happening to the 1, so I'm going to write 1/4, 1, and then I'm going to write 1, 0. And what I'm going to do here is I'm adding 3, because that's a horizontal movement, add 3. And then right here, this is a multiplying by a half, multiplying by a half. And so I'm going to go ahead and graph that. That's going to be 3 and 1/4. So 1, 2, 3 and 1/4, and then up a half right there. And then I'm going to do, this one is 4. 1, 2, 3, 4. And then this is going to be 0. Okay, now remember that this, normally the asymptote was y, the y-axis, and it has moved over 3 units. 1, 2, 3. So it's moved over 3 units here. So this is what the graph is going to look like. All right, let's do it again. Here is my parent function, and I know that this answer is going to be 0, and this answer is going to be 1. So I'm going to write these down. And this is a horizontal movement, so I'm going to add 2 to both of them. And then here I'm going to times by 2. So this is going to be 3, 1, 2, 3, 0. And then this is going to be 5, and then up 2. Now remember that the vertical asymptote has been moved over 2 units. So I'm going to move it over. And then this graph is going to look something like this. Okay, over here, I know that the parent function right here, 1/2 to the 1/2 to what power will equal 1/2, and that'll be 1. And then 1/2 to what power will equal 1, and that's 0. So I'm going to take this 1/2 and this 1, 1 and 0, and what I want to do is I'm going to subtract 1, because I'm going backwards. Subtract 1, because this is a horizontal shift back 1 unit. And over here, I'm going to multiply by 1/4 and then subtract 5. Multiply by 1/4 and then subtract 5. Okay, so this is going to be -1/2, and then this is going to be -4 3/4. 1, 2, 3, 4. And then this is going to be 0, and then 0 and -5. 1, 2, 3, 4, 5. Okay, now we know that the vertical asymptote has been moved over 1 unit. And then I can go ahead and draw my curve right here. Pause and see if you can do the problem. And here's the answer. Pause to see if you can do the problem. And here's the answer.